It is, there we go. Okay, so thank you everybody. Thanks you for joining. What we're going to do now is have a panel discussion with some very experienced and very gracious folks that have a lot of ability to talk about the topics that are valid here. I think that many of them can talk about quite a bit outside of that too, but we are going to try to focus on the interface again between the facility and the specialized liquid cooling type systems. So right off the bat, again, this is the general topic isn't so much the ACS, the actual the technologies, the immersion or rear doors, what have you. It's really how you tie these into a facility, both existing and new. So that's the topic in general we're going to try to hit on here. For today, we have 4 folks here again. We've got Jason Rafkin. He is the Vice President of Solutions Engineering for Stack Data Centers. John Gross, who you might have just heard on his presentation of implementing data center liquid cooling on a very large scale with really high densities. We have Tim Chambers, who is a recipient of the 2020 Data Center Dynamics Energy Smart Award, and Vali Sorrell, who's a principal hardware engineer with Microsoft, but was also with other design companies in the past. So a lot of on the ground experience designing these systems. So again, the parts we're going to talk about here are the interfaces. Whether or not we have things in the middle here, for example, chillers and CDUs, and how that ties in with the remainder of the gear. So with that, let me get this going here. We, from a discussion perspective, also going to bring this up again. This is the chart that we've been working on. This will be SI when it's finally completed. With a version in IP units as well. Just giving, this is a rule of thumb max heat transfer equation. So you say, all right, I've got a pipe that's 5 inches. I'm going to use a 10-degree delta. And therefore, I could theoretically transfer about 400 kW of heat from this source to my downstream equipment. This is going to be an output of our discussion. And finally, we'll leave it with what we're talking about and what we're going to ask these folks about. So the 3 main topics we're going to hit are adding liquid loops to existing solutions. So on that, I'd like to say, Jason, you are an owner of a bunch of data centers here and have experience with building them and also changing them over time. What have been your experiences there, in particular with respect to raised floors and versus slab floors, which is there's quite a few more slab floor data centers coming out for a host of reasons, and they present a different challenge. So please speak to that.
Sure. Thanks, John. Good morning, everyone. My name is Jason Rafkin. I'm Vice President of Solutions Engineering for Stack Infrastructure, and we are a co-location provider for hyperscale enterprise clients across the US. We're in 8 markets. So that's a little bit of the background. We have about 10% of our deployment already using rear door heat exchangers, predominantly rear door heat exchangers for the liquid cooling solutions. And we've done it in both raised floor and on slab environments. And working with our clients, we find that the conversation is starting to be raised more and more often. So in the past, it has all been rear door heat exchangers, but more recently this year, we started to engage with clients that were looking for alternate advanced cooling technologies using CDUs and proprietary liquid to chip or bath solutions. So we started thinking about how to best solve those. Our current basis of design is on a slab floor. We do have 14 feet of clear height between the floor and the ceiling. So how can we make that work? And obviously one idea is to bring the chilled water into the data center floor onto the slab, connect to a CDU, and then distribute overhead. And we've done that, and we have several megawatts deployed that way, and we had to address the leak mitigation issues and concerns. There haven't been any, but we had to put those in place just to give the client comfort and the operators. So I think that technology is there. It works, but there's this comfort level that still needs to be overcome. And what we've done is we've actually modified our chilled water design a little bit, our loop a little bit, and we're starting to pre-position taps in our mechanical galleries. And in those galleries, we can use a CDU and transition directly to the liquid cooled solution fluid, and then leave it to the manufacturer, the proprietary solution, to then handle the liquid in the medium in the data hall. And what I found was really interesting from John's previous presentation, he was talking about, one of the points he brought up was the return lines actually adding heat back into the air side equation in the data hall. And that's something, you know, I hadn't thought of before. So that's really good insight. Thank you, John.
Yeah, thank you, John. That was brought up on some of our calls during our weekly calls with especially with higher temperature systems. Immersion cooling, for example, can utilize higher W4, W5 class water systems, and radiation starts becoming an issue. So that's very good. Let's see, the, excuse me, tying in on the return is another topic here that we have up. And I'd like to ask Tim Chambers, have you tied in on return lines, and have you had success with this, and any challenges with this that you'd like to discuss?
Yeah, the return line was it's an interesting challenge in itself, because one of the things we built, we actually did like a cascade solution to do energy reuse. And the biggest issue is obviously you start to reuse the waste heat we did it for comfort cooling. There's times in the year where you don't need to do that, so you do need to feed it back in. So I suppose the real lesson learned, what we did, it was interesting you mentioned the fact that heat losses as well, is we had to monitor the pipework specifically to see what we were actually going back into the cooling system for, to return the water back around the loop. So under normal circumstances, when we were reusing the heat, it wasn't an issue. We found quite a lot of changes during usage as to what that actual return temperature actually was. So we had to be really quite keen on monitoring it. Also go back to the fact that we did a similar solution where we were on a slab floor with overhead pipes. We did get heat loss. So we started getting heat into the data halls, and we actually mixed the immersion tanks with rear doors and used the rear doors to actually stabilize the room temperatures. But it did have to change different times of the year. We had to monitor it and constantly keep changing to keep that temperature right. So I suppose the lesson learned for us was to not assume what your return temperature is going to be. It does change quite considerably depending how the temperatures depend in the room.
Now, Tim, when you tied into these, were you tying in directly to the return line, or were you putting it through a CDU arrangement of some type?
We put it through a CDU.
Okay. All right.
Yeah. So again, we had the CDU within the data hall.
Great. Great. John, one of the points I think that was very impressive, or I would say I would put it also in the category with radiation being one of those things you might not think of right off the bat. How about the pressure issues? In your talk, you talked a little bit about encountering some pressure issues when implementing against an existing set of pumps, not in normal operation, but in some skirt conditions. Could you talk about that a little bit and what the concerns might be, especially with respect to downstream ACS gear?
Yeah, for sure. So, you know, the impact on the ACS gear really depends on whether or not your pumps are separated, your facility side pumps are separated from your ACS by a CDU. But the habit that we get in when we're designing facilities is we look at the steady state operation, and that's our quote unquote design condition. The thing we have to keep in mind is that there's the design condition that we expect to see every day, but then there are events that we know are going to happen during the course of the facility's lifetime. And being critical facilities, not understanding that they cannot go down when those types of unplanned events happen, we have to take those conditions into account when we're doing the design of the facility. So for example, in that separate high temperature plant that we designed, we had, as I called them, building level CDUs that separated the chilled water system from the process cooling that was going out into the data center itself. So we actually kind of had two separate facility water systems there. We did that because of the temperature delta incompatibility between the ITE solution and the chillers. But on the pumps that actually were connecting to and pumping to the CDUs that were being provided by the ITE manufacturer, we had to look at the deadhead pressure of that pump. If we deadheaded that pump, what is the maximum pressure difference that it could generate? And on top of that, we had to look at the makeup pressure to that system, recognizing that that's going to be our minimum pressure to that system. And we had to compare all of that to the maximum working pressure of the CDU that was being provided by the ITE manufacturer to make sure that all those parameters worked well together. Because there is the situation where we have a loss of power to the data center, generators come on, things go through a restart mode, and depending on the failure positions of certain valves. So some of the ITE, when you're talking HPC, a lot of times HPC is not backed up by the UPS itself. And so its control valves will actually close, not open, because it's not demanding water flow. But if you have that kind of ITE solution on the floor at the same time that you have an ITE solution that is backed up by UPS and is demanding flow as you recover from the power failure, now the amount of water that you're trying to push into that loop goes down. There's less demand for it, but your pumps may have deadheaded or may have run up to full speed in an attempt to recover from the failure, at which point you've increased the actual differential pressure downstream and you could start tripping stuff offline. So I guess the gist of it is that as engineers, facility designers, it is incumbent upon us to stop assuming that the everyday scenario, the steady state scenario, is the design. The design is every scenario that we reasonably expect that facility to encounter during its lifespan. And we've got to run through all those traps.
Very good. Thank you. Thank you. Very true. You mentioned in your own talk of having doors blocked open. I've had similar situations, a loading dock. I've had alarms go off and people saying, why is the humidity going crazy? And well, it's because a new cleaning company came in and mopped the entire raised floor, throwing off all the alarms. Valley, elevated temperature loops. Now there is a potential to add dedicated elevated temperature loops to data centers these days, particularly to avoid, well, almost entirely, to avoid compressor use and get your PUE better. Have you done any work like this at your current job or others? And can you tell us any of the challenges of doing and advantages of doing dedicated elevated temperature loops?
Yeah, sure. I can't answer the question about what I'm doing in my current employer.
Okay, understood.
Everything that I'm saying comes from my personal experience in combination of past and current employment. And with John Gross, he and I have been discussing this for quite a few years. Don Mitchell, thank you for bringing me into this. This has been a huge issue for that group within ASHRAE that's been looking at this. So it's a really big deal. And I think we're still trying to find the Goldilocks zone, because when you say high temperature loops, yes, one of the issues is that what you're really trying to do is eliminate the chiller plant. Eliminating any central plant or chiller plant is a good thing, because not only do you remove the energy associated with operating large chillers, you are also taking away certain issues like dew point control, it becomes a non-issue. And it makes complete sense to operate at a high temperature so that you can take care of all the HPC equipment. But like I said, Goldilocks zone. You can't go too high and you can't go too low. You've got to find that happy medium to be able to operate around the clock at all times under all design conditions and all operating conditions so that you can meet 100% of the demand that may be required on the IT side without causing any blips in the operation of the IT equipment. If you go too high in temperature, like if you could theoretically deliver 50 C water, facility water around the clock, because there's probably not a climate on the planet that can't produce 50 C water, but it takes a penalty, takes a hit on the IT equipment, because now the IT equipment is going to be operating at a much higher temperature also. So some of the benefit of having liquid cooling is taken away from that standpoint. You want it cool, not too cool. You want it hot, not too hot. Probably, and this is just rule of thumb, a good starting point for high temperature liquid is probably about 40, which gets you into the W4 range of the ASHRAE, which is really good for maximizing on IT equipment operation, but it's not quite there. It's not quite high enough if you are trying to do heat reclaim. So getting into the W5 range of high temperature, which gets above 45 and above, is a really good place to be if you have a consumer for the heat that you're going to be taking out of your facility. So a hyperscale facility, theoretically 10, 20, 40, 80 megawatts of heat, it sure would be nice to not just put that up into the outside atmosphere and let it go with either dry coolers or evaporative coolers. The idea is if you have a user, great. It's really hard to find those users. It's just not a realistic operation. And in many cases, especially in the US where things are spread out a lot more, the next available user for something like heat reclaim could be 10 miles away. So the practicality of it is removed. If you're in an urban environment, you may be able to find somebody to purchase that heat. I think in Europe, this is more of a feasible solution where everything is packed in a little bit better. But short of running in the W5 range, W4 getting upwards of about 40 C, I think is the Goldilocks zone for normal and stressed operations.
Valley, that's very good. I agree. It'll be interesting to see how the IT equipment and the chips and the solid state electronics change over time, and maybe can go to higher temperatures. But would you mind, before we move on to another major question, just briefly explaining the concept of the W water classes? I know a lot of folks on this call have probably heard of the ASHRAE air temperature and air conditions classes for data centers, but it's probably not as widely known, the water work that's been done recently.
Sure. So as there are classes of temperature, A1 through A4 relating to temperature of air entering a piece of IT equipment, ASHRAE has also created the liquid temperature classification system to serve as rules of thumb or guidelines. There's nothing specifically magical about it, but W1, W2 are the kinds of water temperatures, facility water temperature specifically, not technical water temperatures like something that would be on the IT side of the CDU. So the facility water entering upwards of about 25 C could conceivably use chiller plants to deliver that solution. Like John mentioned in his presentation, using water 20, 25 C, you could still use a high temperature chiller, but when you get above that, you can actually say, I can deliver that mostly with more passive means like cooling towers, closed circuit fluid coolers, evaporative coolers. And so eliminating the chiller is really where you want to be, which is in the W3, W4 range. W3, correct me, John, if I'm off here, but I think the W3 goes up to, is it 32 C, and W4 goes up to 45. And and W5 goes even above that 45 so that you can use facility water to reheat other or sell your heat to other users. So the W classification is a good rule of thumb. It's actually in the process of being modified right now because it's too granular a view on the availability of water. So instead of having, let's say, W3, W4, which has a pretty big step between them, it may actually go to W32 or W40, and then the next one, which would be the W5 range above that. So it may become a little finer in detail so that we can work a little better using these guidelines, the industry guidelines, for really understanding what we can do on the facility side to eliminate the chiller plant, improve efficiency, and in some cases even sell the heat to outside users.
Yeah, so I had a conversation in the last couple of days because, as Valley mentioned, the W classes is being actively reviewed right now by those within ASHRAE TC99, and he mentioned W32, W40s, et cetera. So there's an effort going on right now, not just to improve the granularity of the solution, but also to make it more meaningful to folks. And so what's being proposed right now, but it's not agreed upon yet, is actually ditching the 1, 2, 3, 4, 5 and actually replacing it with the temperature that's at the high end. So what's currently W1, which is 17C, would become W17. So it's 17C water. As part of that conversation, I was actually educated on where the current numbers actually came from. And the W1 at 17C was originally developed because the thought was that anything below that was potentially below dew point, and anything above that was potentially above dew point. 32C was picked for W3 because that seemed to be a reasonable break point for evaporative cooling versus not. 45C for W4 was heat reclaim. And there was some confessions made by some folks on the in the voting members group that 27C was picked for W2 mainly because most of the ITE manufacturers were hanging out at about 27C at the time that classification was created. But yeah, the goal also right now with the renaming is to make it simpler and easier for folks if classes are added or taken away. So that we don't have a situation where we have a W1 and a W3, but not a W2 or something along those lines. So,
right.
Just to add to what John is saying, I never remember the top level of each W. Like I think we know in principle W1 through W5, but I'm glad that John just said that W1 would be up to 17. I never remember those numbers. I know there's a W1, 2, 3, 4, and 5, and 5 is for. I really welcome the ability to remember what the upper end temperature rather than going to the W tables from the ASHRAE book to refresh my brain about what the upper end of the temperature. It's like I said, it's a really useful guideline, but there's nothing magical about it. And renaming it and repositioning them something like what John describes, I think is a really positive step forward.
Yeah, and I think it's worth mentioning that our group in general are trying to align and synchronize with ASHRAE work that's been done, ASHRAE standards that have been established that make sense for us to deal with. And the water and air temperature classes definitely fall within that. Jason, one of the things you mentioned earlier, and one of the things that's actually been quite an active topic on our calls is you mentioned that you're actually adding in taps or proactively putting in taps just in case. Can you tell us where you're putting them and how large you're putting them for, and kind of what metrics you're using to size those?
Yeah, so our typical data hall is 18 to 20,000 square feet, and we have mechanical galleries along either side. And in those mechanical galleries, we have fan walls. So we are placing taps on either side of those galleries to be able to provide initially 1.2 megawatts of liquid cooling. And we're also sizing and operating our chilled water plant to support both air side, because we still need to meet the A1, A2, A3 ratings that our air customers need, and then also be able to provide a water liquid cooling solution. So we do have an elevated, but not an extremely elevated chilled water loop, more around 20C. So with taps, and they're 4-inch taps on them, and with them in both cray galleries, we can actually provide even added redundancy, resiliency to the liquid cooled load by coming off of each branch, the one on the south side and one on the north side. So we've also worked that into our design, and this also has the benefit if we need to subdivide our suites a little bit. We can also use those taps either for liquid cooling or additional fan wall units to provide the same level of resiliency for our clients.
Great, very great. Excellent, thank you. Tim, I'd like to talk about cascade cooling a little bit. I know you have experience there. It's a bit more, I would say, complex. It's kind of it goes into like the one line of mechanical one line that John had shown earlier, but can you talk to reuse in terms of cascade cooling and what you've done with that in the past?
Yeah, so if we go back to trying to, I suppose, raise the temperatures, we built a facility where we were, I suppose, lucky that we could do it as a single line because we made sure all the IT kit was actually in order. The future designs involve multiple loops which do the same thing, but effectively what we do is you use different technology to raise the heat. So effectively waste heat from one is effectively the input heat of the next. And we were able to, I suppose, cheat really, because we planned it out in that way, to work through a multiple range of heat exchangers to lift the temperature. Going forward, we do this in separate loops. So each of the runs goes through and back into its order on a main pipework. Again, go back to tap off points and things like this. What this allowed us to do by going heat exchangers and tap offs, we effectively put different sizes of connections which we could wind up and down, which meant that we could actually use something like a rear door at low temperatures, but later on replace it with something like an in-row running on-chip cooling or even an immersion box. So the idea being that you can actually change these runs out later and actually put the different technology on. But the driver for us was to actually start from quite a low temperature and drive it into, as I say, an energy reuse. So we built it deliberately, as I say, to provide comfort heating within the actual facility itself for the officers as a starting point. And we effectively went from what was traditional hot-aisle containment all the way up to immersion cooling. But we were able to stage it to make that actually happen. As I say, going forward with designs now, the skill is actually creating these loops to link back. And as I say, it works really nicely. It also means that you actually can keep the PUE pretty good on every one of your runs as well, because you're effectively using the next lot of IT equipment to be the cooling for the one before. So it means that your load's a lot better. The issue you do get is go back to the fact of where it is. We were lucky that we were on a business park, so we had a good use of the actual waste heat. On situations where you can't get rid of the waste heat, naturally you're now up at a higher temperature and you're going to have to take that loop back round, in which case that's why on the other designs we break these off. And it was interesting when John was talking earlier about the idea of having separate runs. Again, this is something we've designed where as IT grows, you could go from a separate run to then take it back into a cascade heat. But this is where you'd have to constantly monitor what temperatures were coming from each area.
Interesting. Was that, and when you say separate runs and then eventually potentially connect them, are you talking automated or through piping changes or valve changes manually later?
It would be automated valve changes.
Yeah.
Again, lessons learned. The first lot of valves we tried on this, we had lots of sticking problems. So the valves were far too slow at responding. So it was a case of, we played around with quite a lot of technologies to work out the best route for it. And that was the weak spot of the system, was how fast we could actually open it. The other thing we did on there as well to keep Dr. John Summers happy, we actually wanted to prove the PUE going out into a larger heat source. So we actually put dedicated pumps on there to actually show in the PUE of this happening. And what we found with these, we didn't use them for about 3 months and they just locked. So again, part of the plan was, well, actually these pumps weren't capable. So the thing to do is we had to be really careful of what equipment we put in there, because some of this kit is not made to actually, I suppose, move around as much as we'd like it to do. And it's something we are doing testing on at the moment to make sure we don't fall foul of this on bigger installations.
Thank you. That's very interesting. Locked up pumps at 3 months. That's a problem. Let's see. That brings the whole topic of materials in. Would anybody like on the panel here to talk about pipe compatibility issues? If you've ever seen those types of issues, one of the reasons for putting a CDU in the loop, there's a host of them, but one might be to separate the two types of liquids, and there are liquids that could potentially be a problem or cause seating issues with a valve or what have you. Anybody want to chime in on that one? No.
Well, I think what I can say is that, John, as you know, through the calls that we've been having, and you mentioned it earlier, is that one of the goals for this sub project is to compile and produce guidance, not necessarily to rewrite the handbook, right? And so liquid quality, liquid purity, and materials compatibility, a lot of that information has already been researched by and published by ASHRAE through the TC 9.9. In 2018, there was a white paper that was published that talked about material compatibility quite extensively. And the idea that we have with this group is that where that work has already been done, we want to reference it, and we want to guide the participants in this effort to use that existing work. Among other things, it's going to make it that much easier for things to be plug and play as new players come into the market. Owners decide that they have an existing facility and they want to make some modifications to make it OCP ready. They're not having to go do some weird materials issue or compatibility issue, water pressures, whatever, that OCP requires that nobody else in the industry does. We're trying to align with the industry and say, guys, these are the lessons learned that we have from the whole group. And if we follow this process and we leverage these lessons learned, things become a lot easier for this technology to be deployed.
A very, very good point. And one of the points that was made earlier by Jessica in our introduction earlier this morning was that we don't want to recreate we don't want to reinvent things. We don't want to all the time. And it's quite easy to not be involved with a particular standards body or group, or even know that research has been done on something like this. So I think it's a good thing this group is doing good work and pulling in those standards, ideas, and code for this. IT limitations. I actually like to go into that a little bit more. Valley, you brought up the topic a little bit, but what kinds of limitations are we seeing on IT equipment with elevated temperatures in particular? I know there are limits for both damaging, but there's also throttling that can occur, both wanted and unwanted. So any points you'd like to talk to about that?
Yeah, I'm certainly not the IT expert, so I really rely heavily on those who contribute within my current company and from ASHRAE, where there are a lot of people who really know the IT side of it very well. But I can probably relay a fairly good summation of what they've said over the years. Almost regardless of which liquid cooled solution you're looking at, you're going to end up with a lower junction temperature on the CPU, on the board, than what you would have had with even mildly or not even aggressive air-cooled conditions. Obviously, when you start going with higher inlet temperatures and you're pushing the envelope, there's no choice. When the processor starts getting to a certain high junction temperature, it will start throttling. And I think you can still get a lot more capacity out of the computers, the CPUs, when you're using liquid cooling, even at those higher temperatures. So let's say we're looking at a case for immersion cooling, and some of the immersion, you can actually engineer which liquid you want to use, but let's just put a stick in the sand and say, let's talk about 50C, which is pretty warm You could definitely go higher. I don't think that you're going to be pushing the envelope on the processor's limitations at that level. How about 60? With some higher workloads, it's very possible that at those continued high processing conditions, it may start throttling a bit to protect itself. The temperature at which throttling occurs may be upwards of 80, 90, or even 100 C before it actually starts doing that. And because liquids in general are much better at removing heat than air, you can use those warmer liquids. And that's one of the main advantages of using liquid cooling. You get cooling for free, more or less, just by passively removing the heat to the outdoors. And on the other end, you can get lower junction temperatures to be able to achieve some higher performance. You can even try to target some acceleration of the processors. You can increase the clock speed, for example, if you have enough sealing to work with, which may be doable at 50 C immersion liquid or even 55 C. As you start getting upwards of that, maybe the amount of overclocking may be a little bit trickier, but I don't think we're going to be seeing the same kind of throttling issues going with like mid-range temperatures in liquid cooling as what you would have with cold plate or immersion.
Yeah, and if I could add on to that real quickly, because like Valley, I rely very heavily on my colleagues in TC99 to educate me on a lot of this stuff. We're fortunate to have some of the thermal engineers from the big ITE manufacturers on that committee. And I've had a couple of very interesting conversations with them recently where, you know, Valley mentioned the junction temperature multiple times. That's the critical temperature for the processor. When we're thinking about ITE and we're thinking about data centers, we think about a CDU as a heat exchanger, a chiller as a heat exchanger, a cold plate as a heat exchanger. Well, the case of the processor is also a heat exchanger. And a lot of the processor manufacturers and chip manufacturers are starting to run into issues with getting the heat flux across that case temperature, because the case temperature is what's getting affected by the immersion solution. But if it can't extract the heat out of the junction of the processor, then we haven't really gotten where we need to go. And once that barrier of performance to cooling solution, i.e. air versus water, was really officially crossed in early 2019, the push for increased performance has driven processor power up more and more and more. I mean, it used to be that the high-end processors were 165 watts, and now you're seeing, 400-watt processors on the market all day long that say you can't, cool these with liquid. So I bring this up because, the junction temperature is what matters to the chip. Based on your workload and what market you're working with, you might see that with liquid cooling that the temperatures are going to go up and up and up and up and up, and you can use more heat recovery. But in compute intensive workloads like HPC, the manufacturers are actually all predicting that the temperatures are going to start going back down. And a lot of it has to do with the performance and the heat exchange across that case and needing to get the fluid temperature colder in order to keep those processors cool. And I did some work a couple of years ago with some two-phase immersion. And we actually had a client ask us not how hot can you run two-phase, but how cold can you run it, because they were trying to overclock their IT as hard as they possibly could, which puts that much more stress on that chip case heat exchanger.
But let me also add to what John was just saying, because I just happened to have been looking at some notes from an ASHRAE winter conference of 2020. John, I think you were there, and I think one of the thermal architects that we both rely on very heavily actually presented this. So I'm actually looking at my notes from that. So he's got, for certain CPU or class of CPUs, starting initially from 75 watts, going up to 600 watts. And at the 75 watt range, it's perfectly acceptable to use A4, which gets, I think, close to like 35 C entering air temperature. Correct me if I'm wrong. Like I said, I never remember the limits of that. But interestingly, as the density of the CPU increases, they really want to see A2, which is considerably lower in temperature. And then as you start introducing liquid cooling, it's again okay to go with W4 conditions. But as you get upwards to that 600 watt condition for one particular CPU, they're really asking for W2. So it's contrary to what logic would tell you, that as it gets hotter and more powerful, you can start using the warmer air, warmer liquid, but it's actually opposite from what the thermal architects are actually asking within the industry, saying, yeah, we're starting to see the limit of what our processor can do. We do need cooler water or cooler liquid or cooler air.
Great, great. We've got a couple of questions here, so I think we're going to transition to some questions. One of the questions is directed at Tim. Tim, the question is, what cooling temperature, what cooling technology at the rack level are you using at your company?
On conventional racks, we started off using U systems rear doors and U systems in rows. We've got a set of Rittel LCPs, and we use a ZutaCore on-chip cooling. And then we moved on to the Asperitas immersion cooling.
All right, so those are the components that would give you your cascade?
Yeah, so that's how we effectively work from a, if you imagine our starting thing was a typical hotel containment using U systems in rows. So this was our low powered rack. So we start from that point. We then rolled into a more, I suppose, an higher temperature based in-row solution using the U systems once again, but for higher temperatures. We then went into the LCPs, which again take the temperature up again. So these are the Rittel units where, rather than anneal the actual, if you like, the hot tiles physically inside the rack, we then went on to on-chip cooling there to then take that onto U systems rear doors, and then finally onto the Asperitas immersion system. As I say, we're very lucky we were able to do it as one loop because we were able to build everything in the right order to do this. But it was a great way of testing between everything, so we could then design, as I say, as a way of elevating and taking different units in and out on different circuits.
Certainly very interesting. Thank you. Let's see, another question that's come in is, if the chips don't have a problem with higher temperature and immersion cooling, why would we not work with 70 to 75 C, which would make regeneration possible? Regeneration.
So I think what they're talking about there is possibly taking the very high temperature return water that you would get off of such a system and putting it into something along the lines of an absorption chiller. And I will tell you that when I was doing the work with the two-phase immersion a couple of years ago, one of the national labs in the US was actually doing precisely that with immersion, with absorption chillers at their facility. I'm not sure if I'm allowed to say who it is, so I'm not going to. But they were running, I believe their supply water going into their facility was on the order of 55 to 60 C. And so they were seeing return water temperatures up around 80 to 85 C coming back, and they were running absorption chillers that were cooling the admin space attached to the data center.
Very interesting. Okay, great. These were absorption, not adsorption chillers?
They were lithium bromide machines. I sometimes get the D and the B backwards on that, but yeah.
Let me also add that probably the worst enemy of taking that approach is having an irregular or non-continuous load. So if you're running a chiller, like an absorption or adsorption chiller, as the case may be, whichever of those chillers, if you have a high daily load and then it drops to almost nothing at night, it becomes a little bit more of a challenge to operate on a regular basis. The best that you can do is find a constant guaranteed user for that load. So I think an industrial process might be a more ideal time, not a better or worse, but just a more ideal type of application, because then you can run continuously without worrying about balancing your heat flows. If you run very hot and you're able to sell that heat that's great. But if you can't sell it, now you have to reject a lot of heat, and that becomes a bit of a challenge. And the one thing that data centers do not like is changing loads. And the IT load may not change, but the heat rejection is going to go up and down. It's going to go up at night. It's going to drop in the day.
Yep. And the other thing that I'll add is, as we've been going through the conversations today, even since the opening, our focus has been on processors. Our focus has been, we haven't even really talked about GPUs and DIMMs for memory, and workload dependent. Those different chips can have different requirements, or they can be the critical temperature in the solution. What we haven't talked about is things like networking and storage. And one of the challenges that you run into when you start factoring those pieces in is a lot of times the networking and storage hardware is not compatible with those ultra high temperatures. One of the other colleagues that Valley and I have on TC99 is one of the head engineers for one of the storage hardware manufacturers. And I had this specific conversation with him when I was doing the work on the immersion. And basically what he said is that once you cross about 45C or so, and you start going above that, you start seeing more faults on drives, whether it's an SSD, whether it's a hermetically sealed spinning drive. You start seeing those faults increase. So even in solutions where the processor hardware, whether it's GPU, CPU, et cetera, it may be able to handle 65, 70C. You need to be cognizant of the fact that your networking and your storage may not be able to, and you may have to have a supplementary system that can handle those.
Yeah, taking that point, we had a hyperconverged cloud platform, which we run all the processes in the immersion box, but the network and the spinning drives, we actually ran in a high performance rear door. Mm-hmm. So we did it that way. So the networks and the spinning drives were all in rear doors, but the actual true processors physically worked in immersion. It was for exactly the same reason. The spinning drives and the networking equipment wasn't compatible with immersion.
Very good. Very good. Do we have any more questions? Let me just check if we have any more questions here queued up. I do not. This is more a comment than a question, but Cosimo Pecchioli from North Laval has asked, when we talk about liquid cooling, we should really separate the discussions into performance improvements or energy savings, depending what you're trying to achieve. Even if the goals are the same, relatively the same, they do have different aspects to them. And I think it's a good point. I'd love to have them both be optimized, but it's not possible necessarily.
John, can I just add a little to that, because I agree completely. But there's a third issue that we seem to forget. I brought it up when we were having our weekly discussion this past week. We tend to lose sight of the reliability issue. And I think when you're talking about liquid cooling, theoretically, the number of steps required to move the heat from the IT to the outdoors to where you're rejecting it is probably the minimum that it can be, short of going with something like a canopy over your IT cabinets in an open air environment. I mean, that can't be simpler. It's not ideal because you don't have complete control over the outdoors, and you don't have complete control even in a airside economizer type of operation.
It has been done.
It's done all the time. But then when you start doing direct evaporative cooling with a 100% economizer arrangement, you introduce the issue of high humidity and dew point control, and the control strategy becomes more complicated. Even if outside air economization is just simple, just you use fans to bring air in, you distribute it, you use fans to move the air out. That, in terms of number of steps, couldn't be less. With IT, liquid cooled IT, you're in a similar situation, but you're basically using a pump to move liquid through the IT equipment, through a heat exchanger, and then fans to reject it to the outside. In terms of simplicity, fans and pumps are gold. There's nothing more simple than a pump and a fan. There's nothing else that could be replaced as easily as a fan and a pump. So if something goes down, it's easy to swap it out within an hour or two, and not much damage done at that point. When you start introducing, even if you're doing the same level of steps to remove the heat, when you start doing alternate levels of control where you can swap to your heat rejection device, so you can do it like this in the daytime, you can do it like that at nighttime. Now you've added complexity. If you add a chiller plant, forget it, all bets are off. There's nothing more complicated and flaky in the general scheme of things than operating a whole chiller plant or any kind of central plant that serves a campus situation, because campuses really create a challenge. What John was saying before is absolutely true. You've got your data center that is now getting chilled water from a central plant. You've got chilled water, which is problematic enough already. You've also got the chiller plant that has these massive, like you said, 500 horsepower pumps that generate too much pressure. It's got to be kept simple. The simpler, the more reliable it'll be. And not only will it be more reliable, it'll be super efficient if you're running at a relatively high temperature. So it's a two deal issue: energy efficiency and reliability that needs to be considered.
And I was actually gonna tag on to a comment you made earlier, Valley, when you were talking about the efforts to try to elevate the temperatures. To me, the efficiency is part of the reason to go to the elevated temperatures, but the big one, if you can get there, is to get rid of the chiller plant, because as you said, simplicity is reliability. There's data all over the place out there about the fact that the vast majority of unplanned outages in data centers happen due to human error. Well, one way to reduce human error is to make the systems much simpler to operate than a water-cooled chiller plant with economization, primary, secondary loops, so on and so forth. Not only are those systems expensive to build, they're expensive to maintain. They're going to be less reliable just by sheer virtue of the number of moving bits and pieces that they have, the amount of controls code that has to be written in order to get them to work, the number of failure scenarios that have to be Murphy'd by the design team, the programmer, the commissioning agent, so on and so forth. And so by simplifying all of that, you're really driving, your reliability up. And to Valley's point, and I hate to say this as a design consultant, right? But if we can, but if you go to liquid cooling, you're getting rid of the CFD modeling of your aisles and your racks and all that other stuff. You're really down to hydraulics. And if you can do that hydraulics without a chiller plant, then to Valley's point, you're dealing with pumps and fans. Yes, we still have to make sure that things like the network and storage are taken care of, but the facility can really be simplified quite a bit, which at the end of the goal, especially if you're a colo provider, and I'm sure Jason can attest to this, anytime you see your risk go down, your SLAs are feeling a little bit more comfortable when you can drop that risk.
No doubt.
Yeah, no doubt.
Yeah, well said. Well said. Let's see if we've got any more questions here. Oh, we do. Sorry. All right. So it looks like we have to end the session. So thank you, everybody, for attending. This was great conversation. I learn from every one of you every time I hear you speak. So thank you very much, and we'll talk soon. Hopefully, join our weekly calls. I want to just go over here and to say again, please join. Just listen. There's a lot of smart people on these calls. You can learn a lot. You can give information that you've learned. Experience is key, and we would appreciate the help.